My name's Eric Brandwein, and I'm a distinguished engineer with the Amazon security team. Today, we're going to talk about some of the systems and processes we use when handling inbound API requests from customers. The title is a reference to a talk that I gave at this conference 9 years ago. That was entitled A Day in the Life of a Billion Packets. It was talking about the internals of VPC. Even back then, we handled way more than 1 billion packets in a day. So it was a fun title, but it was numerically inaccurate. This title is also inaccurate. The most recent public statistic is that AWS IAM handles 500 million requests per second. A quick bit of math leads you to the fact that we must handle trillions of requests per day. This is one of the most scaled systems on Earth and one of the unsung heroes of AWS. And today, we're going to take a closer look at it. Anytime you're dealing with anything over a network, anything that any security person has touched, these two topics come up. Authentication is making sure that the party is actually who they say they are. Do I have Eric Brandwein's driver's license? Authorization is determining whether or not the person that has that driver's license is cool enough to do the thing. I'm usually not that cool. Most talks in this area gloss over authentication. They assume that authentication is handled, it's a solved problem, and then they spend a lot of time on authorization. Which is fine. Authorization is a fascinating topic. It's worth being dug into, and there's a lot that can and should be said about it. However, in this talk, we're going to flip that script on its head, and we're going to spend most of our time talking about authentication. It turns out this can be fascinating as well, and the way that we do it at AWS is unique and interesting. In order to fit in the time allotted, this talk is necessarily going to gloss over a lot of details. In particular, pretty much everywhere that you see our system propagating keys, we're also propagating policies. Even though we're going to focus on authentication in this talk, clearly we also perform authorization. In order to authenticate people, we're going to need to build a cryptographic protocol. You've probably heard of cryptographic primitives like AES or elliptic curve cryptography. Those are the fundamental building blocks, but they're not generally useful. They tend to be very narrow in their application. So these primitives are built up into higher and higher level constructions that perform ever more useful things. Rather than something simple like given a key and a fixed size message, produce a fixed sized output that's encrypted, you get given a key and an arbitrary sized message, produce an arbitrary sized output that provides encryption and integrity protection. However, even these building blocks don't fully solve most real world problems. The top layer of this stack is a protocol, a cryptographic protocol. This is the complete specification of every operation that you need to perform in order to complete whatever task that you're trying to complete, ideally in a way that protects you against all of the threats that you've specified. Every layer of this stack is hard. If you read the cryptographic papers, it's pretty rare that one of the underlying building blocks is broken. Much more often, it's the gaps between the building blocks where people find problems and things start to fall apart. Making your own cryptographic protocol is hard, it's expensive, and it's not something that we undertook casually. We did a ton of design reviews, consultations, penetration testing, and more to maximize the odds that we were going to get this right. It's traditional, when discussing a cryptographic protocol, to model it as a conversation between two parties, Alice and Bob, A and B. Randall Munroe published this comic at exactly the right time, so please enjoy. Anyway, we're going to break from tradition in this talk. We've got Alice, but Alice doesn't want to talk to Bob. She wants to talk to the cloud. So here's the cloud. Alice needs to talk to the cloud, of course, and we need to make sure that it's actually Alice that's talking to us. Now, you're thinking, Eric, this is a solved problem. And indeed it is for some definitions of solved. The most common case is logging into a website. So we've got a website. And Alice has some sort of client, most likely a web browser. She browses to some website and is told, who are you? And her browser is automatically going to go redirect her to some sign-in endpoint, so a login endpoint. Her browser is going to render a username and password dialog for her. She's going to answer these challenges. And that login site is going to return to her a cookie, a tiny little bit of data. Her browser is going to squirrel this cookie away. And then she gets redirected back to the website, but this time she includes the freshly minted cookie in her request to the website. The website can validate the cookie, and like, hey, welcome, Alice. We've successfully authenticated Alice. Now, an important bit of context here is that when we initially designed this system, it was 2006. that's a long time ago in the real world, but it's like centuries in computer years. Most of you probably weren't even born yet. Netflix wasn't a streaming company. Mobile phones were incredibly different. The internet was much safer. But TLS was not widely used. TLS is transport layer security. That's what we call it today. We used to call it SSL, secure sockets layer. That's what was in use at the time. It was expensive, cryptographically, computationally expensive on both the server and the client side. And so because we have a lot of clients that just pop up, make an API call, and disappear, they can't amortize that TLS handshake across many requests. They'd have to make that TLS connection for every single call. And when you consider that we have a lot of embedded clients, things that have constrained CPU, constrained power, constrained battery life, that computational overhead could potentially be completely unacceptable to our customers. So in the internet of 2006, mandating that every API call use TLS wasn't a starter. So because we couldn't make all of our customers use TLS, we had to offer clear text endpoints for some of our APIs, and that deeply informed our design. So maybe we don't want to use that cookie protocol, but surely this is already a solved problem, right? So we'll just give Alice an asymmetric key pair. In most implementations, the public key is going to be encoded in a certificate, an X509 certificate, the kind that you use to secure a TLS endpoint, and a private key. The private key is exactly that. It's a secret. It's private. Alice must not share it with anyone. The public key can be shared freely. And what you can do with these is you can use the private key to sign a request that generates a signature. And so Alice can make a call to her provider asking for a cloud, please. And she's going to include the certificate. This is an assertion of her identity. Again, this is public data. And the signature. She's going to send it to the company. They're going to verify this API request. Given the certificate, they're going to check that the certificate was issued by someone they trust, that it's still valid, all of that stuff, that it's associated with Alice. Then they check the signature, which they can do given only the public key. That checks out. So they're going to tell Alice, OK, this is great. So we're good, right? I mean, this is a great protocol. One very nice property of this protocol is that we've got a signature over the entire request. So if for any reason Alice's request is tampered with, whether it's malicious or a fat finger or a cosmic ray, Alice is now asking for 2 clouds, but she signed for 1 cloud. So she's going to send this to the provider. The signature validation is going to fail, and the request is going to be denied. This protocol, with a signature over the entire request, protects us against an eavesdropper looking to steal the keys. In the cookie protocol, if I eavesdropped on a request, I got your cookie, I could then use that cookie in future requests. In this protocol, I eavesdrop on the request, I get the signature is bound to the request, I can't use it on different requests. But it's not a panacea. In this case, everything's working correctly. Alice signed for 1 cloud, Alice is requesting 1 cloud, the cloud provider has said, yep, that's cool, but we have an eavesdropper. The eavesdropper pulls this off the wire. Now, they can just send exactly that same request. It has a valid signature, it's going to validate at the provider, and it's going to succeed. Now, in this case, Alice is paying for 2 clouds rather than just 1. That may be nothing more than a nuisance. But if this is something like resetting an administrator password, that someone has taken the request and replayed it, then that could be a real serious security problem. And this is called exactly that, a replay attack, because the adversary is just replaying a valid request that they obtained. So in reality, the string to sign in the protocol isn't just the request itself, it's going to contain a timestamp. So Alice is going to sign this new string. There's actually supposed to be a full timestamp there, but I'm not very good at PowerPoint. So to verify it, she's going to send this request, which includes the timestamp and the new signature. We're going to verify it. This signature checks out. This was actually signed by Alice, or at least someone in possession of Alice's private key. But then we're going to make sure that that timestamp is good. And since the timestamp is good, then we respond success to Alice. The reason that I'm saying good here and not exactly the same is that you can't assume that two arbitrary machines across the internet are going to have closely synchronized clocks. And so you've got to have a little bit of splay time in there in order for things to work in the real world. And in practice, we found that a value of single-digit minutes is typically reasonable. I don't actually want to derive a full-fledged signing protocol here live on stage. I just included this bit about replay attacks and timestamps to illustrate how the simple, obvious things often fail to work in practice. Like all cryptographic protocols, these signing protocols are really, really difficult to get right. And anyone that wants to dip their toe in these waters would be well served by reading the papers about the flaws that have been discovered in various protocols. Some of you, for example, may be thinking like, hey, he used a semicolon to separate the request from the timestamp. What if the request itself includes a semicolon? What's the parser going to do then? Regardless, this looks pretty cool, right? Like Alice can authenticate herself. We've got a signature over the entire request, so it's tamper evident. We've got replay protection, and we can keep layering on from here. But remember, it's 2006. The overhead of TLS is the reason that it's not widespread, or at least one of the reasons. A 2006 computer is slow by today's standards, and it's specifically the asymmetric cryptography, the signing operation, that's expensive. The protocol that we just described is built on asymmetric cryptography. We could eat that on our end. Maybe we'd pass some of the costs along to our customers, but our clients may not be able to sustain that load. If we require every request to be signed, that is a signing operation, and RSA signing is more expensive than RSA validation. And the laptop, I have an M1 MacBook Pro, and that laptop can do about 600 signing operations per second, single-threaded. So that's an entire core of my laptop. It's less than 1,000 DPS. This is a tough trade-off. So to sum it all up, every request is signed per request signature. That means that the requests are tamper evident. If someone has changed a request, we will be able to detect that when we're validating the signature. And requests can't be replayed outside of the replay window. And the protocol is stateless. There's no need to go to a sign-in endpoint or some sort of token exchange. You pop up, sign an API call, send it off, shut down. So we've achieved all of those goals, but the cryptography that we've chosen is expensive. That's the fly in the ointment. We're so close, but this isn't going to work for our use case. So what now? In order to solve our carefully constructed conundrum, we need to introduce a new cryptographic primitive, the hash. A hash algorithm is also known as a digest. All it does is it takes an input of any size and it maps it to a fixed length output. There are many algorithms that do this that serve many purposes, including error detection and correction. But in this case, we're specifically concerned with cryptographic hash algorithms. In a good cryptographic hash algorithm, the output gives you no information about the input. One way of saying this is that if you flip one bit in the input, approximately half of the output bits will flip. And it has to be hard to reverse, and hard here has a formal definition. It's not impossible to reverse because you could just keep on guessing inputs until you got the same output. You could brute force it. So hard in this case means that no one has discovered a way to reverse the hash that is faster than brute force. And they are quick. They are incredibly fast. That same M1 MacBook Pro can run SHA-256, which is a modern hash algorithm, bright and shiny, at more than 2 gigabytes per second. They're wicked fast. So the reality is that we're already hashing. So we talked about Alice generating a signature over this long message, but that's not what you do in practice. The RSA signing algorithm is slow, and if you're trying to sign an arbitrary length message, it greatly complicates things. So in practice, what you do is you use a hash algorithm to turn the arbitrary length message that you're signing into a digest, and then you sign the digest. And so in that protocol that we just described, where we're using asymmetric keys, we are already hashing. We're already paying the overhead of the hash. And so it's basically free. But a hash just takes an arbitrary length input and maps it to a fixed length output. It's not a signature. How do we turn this into a signature? The answer is that we need another cryptographic construction that goes by the name of HMAC, or hash-based message authentication code. Here's a simplified definition of HMAC. In reality, the two uses of the key on the right side are XORed with some constants, and there's an extra key derivation step that I skipped. You should not implement cryptographic primitives based on my slides. It looks complicated, but it's actually really simple. We take the key, we concatenate it with the message, just string concatenation. We take the hash of that. This can be a data-intensive operation. The message can be of arbitrary length. This is approximately the hash that we would have had to do in the asymmetric case. And then we perform a second hash with the key concatenated with the output of the first hash. This is going to be incredibly quick. It's two fixed-length inputs, the key and the result of that first hash. And so this is an incredibly fast operation. You need this construction because if you just did that first hash, the key plus the message, you're vulnerable to things like extension attacks, where if I've got the message and the HMAC, I can add to the message and I can add to the HMAC. And so this construction is about 26 years old. It has been deeply reviewed by cryptographic experts all around the world. This is not an Amazon thing. And to date, no one has found any issues with it. MD5 is an old and broken cryptographic hash algorithm. You should not be using MD5 for anything. As far as we know now, HMAC MD5 is still secure. So for 26 years, this has been working well. Here's an example. I'm using secret as the key and shh, don't tell as the message, and that's the output. I've added an H to the message. You can see that the next hash that we generate is completely unrelated. I've changed the C to a K. Again, completely unrelated output. And then here, I've changed the capital S to a capital R. And this is interesting because the only difference between the ASCII representation of a capital S and a capital R is that the least significant bit in R is 0 and it's set in S. So this is a 1-bit change in the input, and you can see that the output is completely unrelated to the previous output. And the task that an attacker has to handle is, given the message and the signature, figure out the key. And to date, again, no one has found a way to do this that's faster than brute force. So let's put this into practice. Rather than a certificate and private key, Alice is going to have a single secret that's going to be shared with her provider. She uses this to sign the request via HMAC. And once again, she includes the signature in the message that she sends. She does not include the signing secret. On receipt, the cloud provider has to do exactly the same signature generation. They check to make sure that it's exactly the same signature output, checks that the timestamp is good, and now, since everything lines up, okay, we're in. So where are we? We swapped out asymmetric keys for an HMAC with a shared secret. Where does that leave us? We've maintained all of these properties that we liked about the previous protocol. And now the crypto is cheap. This is wicked fast. Even on a 2006 computer, HMAC is fast. And one of the nice things about using HMAC is that while it is affected by quantum computers, it is way less serious than it is with asymmetric algorithms. If you're using sufficiently long keys for HMAC, as AWS does, then based on current research, HMAC SHA-256 remains quantum safe. However, we've got symmetric keys. The key has to be shared with the provider. And if the key is shared with the provider, that service could then sign any request as Alice. So we've fixed a bunch of stuff, but we've introduced one more problem. So now that the groundwork is laid, let's dig into the actual system that we built. We've still got Alice, and she's going to be starting out with her web browser on her laptop. And let's say that she just created her AWS account, so she's got a username and password, right? And an MFA token. You all have the good taste to come here, so I don't need to say this. I'm sure you're all already using MFA. But if you're not, if you go down to the AWS booth at the security and identity desk, they're handing out free tokens. You should do that if you don't already have one. Alice wants to talk to the cloud, but now we're going to have to zoom in and look at the innards of the cloud a little bit. The first thing that Alice wants to do is create an S3 bucket. So to do that, she's going to have to sign an API and send it to the S3 endpoint. Of course, she doesn't have API keys yet. The way that you get these API keys is through the AWS Management Console. This is the web-based interface to AWS. So that's the first place Alice goes. But she shows up there, she's unauthenticated, so she gets punted over to sign-in, where she answers the authentication challenge with her MFA token, and that gives her back a cookie. This is exactly the protocol we started out with. Now, Alice can authenticate to the management console. She includes her cookie, so the console knows who she is. And this is always, always, always conducted over TLS. All access to IAM and the management console has always been TLS protected. And to create a user, we have to interact with IAM. This is the Identity and Access Management Service. This is where you configure users and roles, policies, and API keys. So on her behalf, the console is going to call IAM, and it's going to create a new IAM user. She's requested that this user have API keys, so IAM needs to create those keys, returns it to the console, and the console is going to return it back to Alice. So let's look at what those keys look like. The first is the access key ID. This is a key in the database sense, the primary key for this credential pair into our IAM database. It doesn't mean anything. It's not used in any cryptographic operations. It's just passed back to the service so we know which key you're using to sign. They're not secrets. They don't mean anything. They can't be used to access anything, and they have no internal structure. The second there is the secret access key. This is, of course, a secret. It's used as an HMAC key, and it needs to be kept secure. However, it too has no internal structure. It's just a blob of entropy. This is the only time that you can get these keys. If you lose them, if you forget them, we will never let you retrieve them from our APIs or from the web console. Go create new keys. This is a real set of security credentials if you want to screenshot it. I created an IAM user to write this talk and then immediately deleted it. So Alice can grab her SDK in her favorite programming language, and she can configure it with these new keys. She's got everything she needs to make API calls. So she crafts the API call to S3, she signs it, she sends it to S3, and now we've got a problem. S3 has to validate this request. One option is we could give S3 Alice's key. S3 could validate that request, but then again, S3 could sign any request for Alice for any service. That's unacceptable. And so another option is that S3 could call IAM, and IAM could verify this API call. And in theory, this would work, but it's not really what IAM should spend its time doing. Request verification sounds like a high-scale and highly separable task, something that's going to scale in its own unique way. And so this makes it a candidate for being its own service, which is exactly what we did. So I'd like to introduce you to the Auth Runtime Service, ARS. This is an internal service. It's not directly called by customers, but it is one of the most heavily used services in AWS. It is used for authentication and authorization of inbound API calls. So every change that's made in IAM is denormalized and propagated to ARS. So now S3 can call ARS and say, is this API call okay? ARS can check the signature on it, say, yep, this really was signed by Alice, respond back to S3, and S3 can respond back to Alice. This theme of restricting access to credentials, restricting privileges that our services have, is a common one, and it'll keep coming up in this talk. It keeps coming up in the design of our services. One possible concern that you may have is that this database of keys that we're creating in IAM and ARS is incredibly sensitive. And that's true, but it's true whether these keys are symmetric or asymmetric. A confidentiality problem with this database is going to mean that you get access to customer policies. You get to map out where they potentially have weak spots. An integrity problem with this database means that you can change passwords or API keys or policies. This database in any system, not just AWS, but any system that has an IAM service, needs to be protected incredibly carefully at the highest level. And so we do that. This is the most locked down system at AWS, and we treat it with due care. Anyway, this is it at a high level. This is how AWS worked until late 2011 or early 2012. If we zoom out a bit, this is Earth, obviously, you can see all of our regions in various places. And we've been looking inside US East 1, which has IAM and ARS. However, if we look at something like EU West 1, this is in Dublin, Ireland, you can see that only ARS is there. Likewise, AP Southeast 1 in Singapore, only ARS is there. IAM isn't deployed there. All IAM changes, user and role creation, policy updates, things like that, to go through the control plane in US East 1, and then they get propagated out globally. This separation between control plane and data plane, where all of the request validation happens, is another reason that we separated IAM and ours into two separate services. And so just like IAM in US East 1 is propagating to ours in US East 1, it's also propagating to all of the other regions in the AWS standard partition. And there should be many more arrows here, but again, I'm not very good at PowerPoint. So there's a bit of history here. Signature version 0 was largely internal. There's no sign of it anymore. It was phased out very early in AWS's history. Version 1 was used only for our first couple of years, but we had a canonicalization issue back in 2008, and we had to fix it. Now, canonicalization is a big word, but it just means making the one true representation of something. Remember, in order to validate a request, the service has to generate a signature that exactly matches the signature that was passed in, which means that they need to have the exact same request that was signed. And it's acceptable for intermediates to reorder HTTP headers or add spaces or things like that. So you have to be able to generate the one true representation. This is hard to get right, and it's an example of the mortar between the building blocks that you can have problems in. So remember back a few slides where I teased, like, what if there's a semicolon in the request? This is an example of a low-quality serialization standard that can lead to canonicalization problems, that can lead to request verification issues. Anyway, what I've described so far is AWS Signature version 2, and we know of no security issues with it. However, let's pop back into US East 1, and we'll take a slightly different look at the region. S3 isn't our only service. We've got lots of them. I've only drawn 4 in here. And every single API call to any of these services is going to involve a round trip to ours. Every API call is signed. Ours is the only place you can check request signatures. This places ours in an incredibly critical position. An outage in ours is a region-wide outage. A scaling problem in any one of our services places load on ours. And if ours then goes into stress, again, it's coupled back to all of our other services. And so this was an awesome design. It survived about 5 years, multiple orders of magnitude in scale, but this coupling between our services was not okay. We had to solve this. And again, this was a great design. I'm respecting what came before, but it was time to do something new. So we've got a system, it's working. There's literally millions of customer keys out in the world, and we can't require that customers get new keys. At this point, asymmetric cryptography is still too slow, and it would require customers to get new keys, so it's not acceptable to the business. But HMAC is symmetric. Got to figure something out there. But it's fast. And so if HMAC isn't the answer, maybe lots of HMAC is the answer. And so that brings us to AWS Signature version 4. This is our answer to the problem that I just posed, SIG-v4. Now, Signature version 3 was never broadly used. It was very early in its rollout, and we had the core idea of Signature version 4. We're like, this is so much better than version 3. And so the only sign that's left of version 3 is a couple of wiki pages internally. There's no existence of it anywhere in our services, and we shall not speak of it again. So if one HMAC is good, what if we have lots of HMACs? What we realized is we could use HMAC to perform key specialization. And this sounds like crypto gobbledygook that engineers use when they want you to stop asking questions and go away, but the underlying concept is really quite simple. We start off with the long-term customer key. These are the millions of keys that our customers already have. We do an HMAC with the string AWS4 and the key against the date. And that generates the daily key for that principal. Then we take the daily key and we use that to HMAC the region name. And we take that service key and we take that region key and we HMAC it against the service name to get the service key. And then we have a terminal HMAC for, again, cryptographic reasons, which is the literal string AWS4 request. So we've got this string of HMAC derivations resulting in that circled blue key at the bottom. And it can look pretty complicated, but you can do this in literally one line of code. And it looks like a lot of HMACs, but again, HMAC is incredibly fast. And so the important thing here is that your SDK does this automatically. If you've used AWS in the past year, your SDK is doing this. You had no idea. The rollout here was incredibly slick. So let's go back to that service diagram and understand why we did this. What does it get us? So we've got Alice. She's going to do her key derivation. Again, her SDK does this for her automatically. She's going to use that final blue key to sign the create bucket request. She's going to send it to S3 in US East 1. S3 is going to send it to ours. Ours is going to say OK, but they're also going to include that fully derived key, which S3 can now cache. Now S3 can do all of the work associated with creating a bucket, and they can return success to Alice. We refused to allow S3 to cache Alice's long-term key because that gave S3 privileges beyond S3. However, this fully derived key can only be used for 24 hours in this region for this service. And so this is safe for them to cache. It can only be used at S3. This is one of the ways that we're driving privileges out of the system. Now, this doesn't look like any savings because we still had to do the full round trip to ours, but if Alice makes another API call, S3 already has the key cached. To this level of detail, this is how AWS has worked for the past 10.5 years. There's a trade-off inherent in the cache that S3 has. The longer it lives, the more value it provides us in relieving load. The longer it lives, however, the longer it takes for configuration values to propagate, policy updates, things like that. And again, in practice, a value of single-digit minutes seems to work very well. And the reason that this is effective is that our customer workloads tend to fall into two very different buckets. The first is interactive clients or things that just pop up, make a couple of API calls, and go away. And a couple of extra milliseconds of latency there isn't a problem. They also don't present that much load to the services. The other is typically large production workloads, where they're just sending a stream of API calls against our services constantly. And in that case, the cache hit ratio is spectacular. Even if someone moved a gigantic new workload into AWS, it would represent at most, what, hundreds, maybe 1,000 keys for millions of TPS? So we're talking about on the order of 3 orders of magnitude reduction in the load presented to ours because of this caching. This is a more complex protocol than we had before, and it's not something that we did lightly. We did multiple rounds of security reviews, penetration testing. We consulted external cryptographic experts. We really wanted to make sure that we had this right. And so if you're going to do this, if you're going to create your own cryptographic protocol, you need to be really convinced that it's the right thing for you to do, and then you need to dive super deep and own it. So as mentioned, version 3 never saw widespread adoption. And June 2012 is when we launched our first SIG v4-enabled service. So this is something just over a decade ago. SIG v2 is still supported in any region and with any service where it was ever supported. We care a lot about backwards compatibility. If you're going to change a website, you just change the website. The colors change, the buttons are in different locations, the human at the browser just figures it out. It is so much harder to change APIs. You've got to adjust a new SDK, maybe there's breaking changes. And so because we know of no security problems in Signature version 2, it's still available to our customers. However, usage has dropped to a trickle. All new SDKs default to SIG v4. And by 2014, we had enough confidence in SIG v4 that when we launched our region in Frankfurt, Germany, it was 100% SIG v4 only. We never supported SIG v2 there. Every region since then has been SIG v4 only. At the time, this was a hotly debated topic, but in hindsight, it was absolutely the right call to make. And in April of 2019, we launched a region in Hong Kong, which is our first opt-in region. The reason we did that is for some of our customers, it was very important that they be able to run in Hong Kong. That was the entire business case for launching the region. But for other of our customers, it was very important to them that they not be able to run in Hong Kong. They did not want their data or their workloads to be present in Hong Kong. And so to solve this, the owner of an account has to explicitly tell us via API call that they want to enable the Hong Kong region. This is a standard AWS API call, so it can be restricted using IAM policies, AWS organizations, and SCPs. Just as with SIG v4 only regions, every region launched since Hong Kong has been opt-in as well. So let's dig in and see what this means under the covers. So we've got our map of AWS regions. And if you look inside US East 1, Northern Virginia, you can see that we've got IAM and ours, and it's propagating locally. And when Alice creates her API keys in US East 1, they get propagated to ours in US East 1. Now Alice can make API calls in US East 1. If you look inside EU West 1 in Ireland, this is our second region. SIGV2 is still going to be supported here. So as we mentioned earlier, there's no IAM in EU West 1, but ours is there. And so the IAM propagator is going to automatically propagate keys, and Alice's key will be made available to ours in EU West 1. So now Alice can make SIGV2 or SIGV4 calls to EU West 1. Now we're going to zoom in to Hong Kong, AP East 1. Once again, IAM is not in this region, ours is. However, the IAM propagator is pushing keys to Dublin, to Ireland for Alice. It's not pushing anything for her account to AP East 1. As far as Alice's account is concerned, this region does not exist. It's as if we'd never launched it. However, Alice wants to create a bucket in AP East 1. She actually wants to take advantage of the region. So she has to make an API call to us to enable the region. And so she turns on Hong Kong. Now we start propagating her keys, but things are a little bit more complicated. Rather than sending the red key, Alice's long-term key, IAM is going to do a partial key derivation here. We're going to do the daily and region specializations to the key, and that's what we're going to propagate to Hong Kong. So the key that gets placed in Hong Kong is scoped to Hong Kong. It can be further specialized by ours in Hong Kong for calls to individual services, but it has no trust anywhere outside of Hong Kong. And again, this is completely transparent to Alice and to our services. This is another example of us driving trust out of our systems, lowering the sensitivity of the keys such that the system is easier to operate and we're more confident that we've got a delightful configuration. And this is an example that I lifted from our IAM documentation. There's two statements in here. The first statement allows the principle to which this policy is applied to call enable region or disable region on AP East 1. So you can opt in or opt out of the Hong Kong region. And then the second statement is just the permissions that you would need if you wanted to do this through the console versus via the SDKs. You could clearly change this from allow to deny, and then whichever principle it was could not enable this region. So let's hit one last topic today, short-term keys. Throughout this talk, I've been referring to that red key as Alice's long-term key, which implies the existence of short-term keys, and indeed they do exist. We'll refer to them often as sessions, so an AWS session or a short-term key, the terms are interchangeable. And this isn't a colloquialism, it's not something that we say informally, we have a very precise meaning for it. A short-term key, or a long-term key, sorry, is valid until someone takes action to make it invalid. But security best practice is that you rotate your keys often, so hopefully your long-term keys don't actually live that long, but if no one takes action, our systems are going to consider these keys to be valid indefinitely. A short-term key is born with an expiration date. They're like replicants. The lifespan can be set when they're created, but it is capped by the system to 36 hours. So compared to the typical lifespan of a long-term key, these are indeed much shorter-lived, hence the name. The real difference, though, is this automatic expiration. And so why would you have this? Why would you introduce this new complexity? One of the most common use cases is federated logins. It's common for large organizations to have some sort of identity broker federated login point, so you can do single sign-on. You authenticate with your corporate credentials, and you can go to the travel site or the customer management portal or the AWS management console. When you authenticate to us that way, we need some representation of you inside of the account, and that is an AWS session. Another common use case is assuming an IAM role. We all know that you shouldn't log in as root or administrator, but sometimes you have to put on your admin hat, and you can do that by assuming a role with the appropriate privileges. In both of these cases, the access is meant to be short-term. It's going to time out at some point, and you want your privileges to trend back towards 0. One of my favorite features for AWS is the ability to pass a role to various AWS resources like EC2 instances or databases to give those resources the ability to make API calls on your behalf. And so let's take a closer look at that use case. I launched an EC2 instance, and I specified that a role named test role should be mapped to this instance. EC2 takes it from there. Once the instance is running, I can contact the instance metadata service and pull the credentials for this instance. The instance metadata service is a web service listening on 169.254.169.254 on every single instance. It's serviced locally. And I hit this particularly long URL. That orange URL is the important bit here. And the result is something like this. Some of these fields are self-explanatory. You can see from the last updated in the expiration header that these keys are good for about 6 hours. And access key and secret key are familiar. Like, we know what those do. So let's take a look at that world map again. Alice wants to launch an EC2 instance with an instance role in EU West 1. Let's walk through the services we'd have to touch if we were to do this with long-term keys. So first we'd have to call IAM in US East 1 and create that key. Then propagation would kick off, and this new key would be pushed to other regions, including EU West 1. It's only after this happens that the keys on the instance would be useful in EU West 1. So now we have to have the IAM service in US East 1 online and reachable. And these keys are good for about 6 hours. So at a minimum, we're looking at 4 new keys for every single EC2 instance in the world. And since they expire, we'd have to go through and clean out those keys. So that's at least 8 transactions per day per EC2 instance on IAM in US East 1. Plus, we're pushing this key to a whole bunch of places that it doesn't have to be. And so this is coupling our regions together. It's adding latency, it's adding cost. We could choose not to propagate this key to anywhere except the places it needs to be, but that makes the propagator more complicated. It introduces the chance for subtle bugs, and it makes the system harder to operate. So it's not something that I'd want to build. It's absolutely not something I'd want to operate. We need a different answer. We need to be able to create and automatically expire sessions at very high scale, and we need to be able to do it local to a region. And so the answer is one of my favorite parts of our authentication system. It's STS, the Secure Token Service. Unlike ours, the Auth Runtime Service, this is a public-facing service. And it's virtually certain that even if you've never heard of it, you use STS. So STS is deployed in every region, everywhere on Earth. This is the building block that lets us issue short-term sessions at scale. And going back to that response that we got from the instance metadata service, there's one field that we haven't talked about yet, that token. And as you may have guessed, the secure token service is all about tokens. You can see that this token ends with SNP. That's because the actual token was about 1,200 bytes long, and the slides were ugly enough as they were. 1,200 bytes is a lot. You can cram a lot in there. So let's pop one of these tokens open. This first set of lines is just internal bookkeeping. There's not a lot to be said about that. Next is the automatic expiration. You can see that unlike the instance metadata response, this is expressed as a creation time and a time to live. But again, it's about 6 hours. And then we have the access key and secret key. These are the exact same credentials that we saw before, just encoded inside of the token. We know exactly what to do with these. One of the cool things that you can do with an AWS session is you can constrain it based on policy. So if there were a policy associated with this session, it would be here in the token. And then the last thing is an asymmetric signature, cryptographic signature, from the STS service saying, I, STS, do hereby swear that this token is cool and valid. That whole thing is then encrypted, and it's passed back to our customer to treat as an opaque blob. So let's put this all together. Alice needs to call STS. She wants to create an S3 bucket, but of course she doesn't have S3 admin privileges. So she's going to do a key derivation for STS. She's going to send her request to STS. STS is going to talk to ours. Ours is going to do a key derivation, validation, et cetera, return the specialized key back to STS for future API calls. And we're going to get back this, a session token. And it's going to have an access key ID and a secret key. Now, the interesting thing here is that STS is going to take this token, it's going to encrypt it up, and it's going to send it back to Alice, where she can then configure it in her SDK. You can see the little clock logo in the little right corner indicating that this is ticking away towards expiry. Really important thing to note here is that STS did not record this session. It'll log the assume roll call in CloudTrail, but it didn't store the session anywhere in AWS. There is no system anywhere in Amazon where the access key ID or the secret key is stored. We create the session, we bundle it up, we return it to the customer, and then we forget about it. And so now Alice has these temporary keys configured. She can make that create bucket call. She starts with the access key ID and the secret key from the session that she just got, does the key derivation for S3, generates the signature for the request to S3, sends it to S3, S3 calls ours. So far, this looks entirely familiar. However, now things diverge. That access key ID doesn't exist in any database. We forgot about it, right? Ours has the mirror to the keys that STS has. So ours can decrypt the token, validate the signature on the token, extract the access key and secret key ID, verify that this session is still active, all of those things. And if everything is good, it can use that access key ID and that secret key to validate the request that Alice just sent in. And so we validate that request. We send the fully derived key back to S3. S3 can go through all of the work of creating a bucket and return success to Alice. From a high level, what we just did seems really silly. We created a session, we gave it to Alice, and then we forgot about it. What Alice wanted to use that session, she had to pass the token back to us. We're using the client for state tracking. By doing so, we can issue sessions at incredibly high rates. When we first built this, we told the pen testers that they would be unable to break us on scale, and the pen testers laughed because they don't believe anyone, and they created 1 billion sessions, and it didn't break us. I mean, it generated a lot of logs, but it did not break us. There is no database of sessions. So you can issue a session in one region and immediately use it in a different region. Our control plane doesn't have to race you to get the keys there in time, because naturally, you're going to get the session from one region, you're going to make an API call to the other region, you're going to include all of the state necessary to validate that API call. Now, again, Eric, you've been ranting that RSA, asymmetric crypto, is expensive. Like, isn't it still a concern? Yes, but one, our cache hit ratios here are incredible. Not only are we caching the derived keys in the services, but ours also has a cache of tokens that it's decrypted. And so if we see the same token presented again in a short window, we're already going to have it decrypted. And it's safe to cache these tokens until their expiration point. And so the result is that we're not cracking tokens very often. And second, our customers only see these as opaque blobs. The only overhead of using an AWS session is a tiny little additional bit, in this case about 1,200 bytes of additional network overhead. That's it. And so we're doing all of the asymmetric cryptographic operations on our side, and we can build our services to handle this load. Was it all worth it? The counterfactual is hard. We don't get to split the universe and play what-if games. But we have a few data points. This is an older paper, but it's a great paper. It's totally worth reading, even today. And I love that serious cryptographic research was published under the title, Here Come the XOR Ninjas. Like when I first went looking for Ty and Giuliano's paper, I was trying to find like the official paper, and I kept finding Here Come the XOR Ninjas. Like, this is the actual paper. The authors disclose a technique that takes advantage of the padding scheme used by CBC cipher blockchaining, the way that block ciphers were built up into being able to encrypt larger messages in SSL v3 and TLS version 1. It's awesome here, but the reason I'm calling it out is that you can extract fixed values. If there's a value that occurs at the same place in a series of HTTP requests, you can use this padding oracle attack to extract that value. AWS API signatures are unique per request. Even if you're sending the same request over and over again, the timestamp's going to change, the signature's going to change. There is no fixed value to extract. So this was the first paper where our public response to our customers was AWS APIs are not affected by this. That was a very satisfying result. There have been more of them in the intervening decade. And so, what have we done? What just happened? At first glance, authenticating requests over HTTP sounds like a deeply studied and solved problem. But the nature of our clients and the unique scale of our business made our use case very different from humans sitting at web browsers, and that led us to a unique and novel design. And as with all designs, we finally saw the end of the runway. But a bunch of smart people figured out how to evolve the system in place with minimal customer upheaval. Literally, all customers had to do was ingest a new SDK, and things just worked. And some of the things that we have in our design look needlessly complicated, but they've actually been really useful for supporting use cases like opt-in regions. They've given us the flexibility to say yes to the business rather than having to say no or having to make some tough trade-offs. And so AWS gets to continue to innovate on behalf of our customers. And even in these slides, the system that I've described isn't simple, and the real system beneath these slides is even more complicated. Despite that, I consider it one of the most elegant things that I've ever had the pleasure of working on, because it's been able to evolve and we've been able to grow it with little to no customer visible changes. The majority of our customers aren't even aware that these things are happening, despite the fact that together they drive over 500 million requests per second. Anyway, thank you very much for coming. It is a delight to be at reInvent in person, and enjoy the rest of the conference.